Dear students, now let's continue from this question number 20. It says, use mathematical induction to prove that, you see, the conjugate of the sum of the first n complex numbers is equivalent to the sum of these n, the conjugate of each n complex numbers for n greater than or equal to 2. So what we need to do here is, you see, we need to apply the principle of mathematical induction. As you studied before, we do have 3 steps we need to apply. So using these 3 steps, we can prove or show that this statement is true. So the proof goes like this. So at the beginning, let's assume that this is named by P of n, just for the sake of, you see, reasoning purpose or for the sake of proving technique. Call this to be Pn because it's written in terms of n. So let's call that to be Pn, proposition n. So P of n. So now the first task is, you see, step 1, and the step 1 is to check for n is equal to 2, because look here, our initial natural number is number 2. You see, this starts from number 2 because whenever addition is mentioned, you must have 2 addends at least. So check for n is equal to 2. That is to say, take 2 complex numbers and observe the conjugate of the sum of the 2 is equivalent to the sum of the conjugate of each of the complex number. So let's check that one. So P of 2 is going to come. So a matter of putting 2 in place of n. So P of 2 makes z1 plus z2. We are considering 2 complex numbers. z1 plus z2 conjugate is equal to, what about here? z1 conjugate plus z2 conjugate. So we need to show that these two are equivalent. If these two are equivalent, then you see, step 1 is now satisfied. So before we continue to the next steps, let's assure that these two are equivalent. Actually, yes, it is true. These two are equivalent because this can be verified by the following approach. Look here. What we can do is call the z1 to be x plus yi and z2 to be a plus bi. Just have arbitrary 2 complex numbers written this form. Then what we need to do is, you see, z1 plus z2 bar. z1 plus z2 bar is going to be x plus yi plus a plus bi. Directly take from these assumed expressions. So we have this. And from this, what follows is, look, the real parts must be added together, imaginary parts must be added together. So x plus a, look, x plus a comes here, and y plus b comes here. So we are now looking for the conjugate of this one. So the conjugate of this is a matter of changing the plus sign of the imaginary one to the minus one. So it will be x plus a minus y plus bi. Can we further simplify this? Yes, we can. Look, this can be further simplified like this. Look, here we are having x, so x minus yi can come here. Here we are having plus a, so plus what follows. Here is, yeah, please correct this by a, please correct this y by a, because it's going to be a minus bi. You see, a minus bi. But what is x minus yi? X minus yi is the conjugate of z1. You see, what about a minus bi? A minus bi is a conjugate of z2. So what we do have here is z1 bar plus z2 bar. You see, so what we said here, P in P2, z1 plus z2 bar is equivalent to z1 bar plus z2 bar holds true. As you see here, look, the conjugate of the sum is the same as the sum of each conjugate. So property, step 1 is satisfied. If step 1 is satisfied according to, you see, the principle of mathematical induction, we have to go to the next steps. Remember, students, if here, you see, in step 1, some sort of, you see, wrong condition is obtained, we could have stopped here. You see, we could have stopped here, but due to is a case where step 1 is right, we can proceed to the next steps in the case of this principle of mathematical induction. So let's go to step 2. In step 2, we have to assume P of n to be true. You see, assume that P of n is true. We have to assume that this holds true up to a certain natural number k. You see, now we have assured here for the first step, we have assured that this is true for 2 complex numbers. Now we are assuming that this idea or this concept or this hypothesis or this mathematical saying, I can say, is true up to what? A certain natural number k. So that is to say that, look, P of k is true. What's P of k? P of k is a matter of changing n by k. Look, P of k is the sum of the first k, the sum of the conjugate of what? The sum of the first is k complex numbers, as you see, 1, z2, z3 up to zk is equal to this one. Look, it has been assumed that this is true. You have to accept this to be true. So using this assumption, we need to come to what? Step 3. In step 3, what we need to do is we have to show that p of n is true for n is equal to k plus 1. Do you remember the steps? We are just applying the steps. In step 1, we checked for the first condition for n equals to 2, and we obtained that to be true. In step 2, we need to assume, or we need to have assumption here, and here p of n must be true. You see, p of n is assumed to be true for n is equal to a certain k, because we have to check for every natural number. But as we are checking for every natural number, you see, we will get a problem of checking everything again and again, because set of natural number is endless, you know. Because of this, you see, we have to assume that this property holds true up to a certain natural number k. And then if you are able to show that the property also holds true for the next natural number, k plus 1, you are done. You can say that see the statement is the entire statement is true by using the principle of mathematical induction. So we are now in step 3. So let's show that this p of n, the one we wrote here, is true for n is equal to k plus 1. That is to say, you see, we are expected to show this one. Look, what have I written here? Look, up to this, you see, up to this we have zk, from z1 up to zk. When we say p of k plus 1, you see, we mean, you see, the conjugate of the sum of, you see, these k plus 1 complex numbers, as you see. And this has to be equivalent to, look, from z1 to zk is already given, but we need to have additional now, zk plus 1 bar. So if you are able to show that this is true, we are done. We can say that this is true. So what follows next is, let's prove this one, let's show this one. But p of k plus 1 is the same as this one. Look, what I did is I just have taken the right expression, as you see. Just take this one. So I'm now on the way to show you that this is going to be equivalent to the left one, this one. So this is equivalent to, look, this is equivalent to this one from step 2. You see, students, from step 2, we can say that this is true. Basically, guys, yeah, please try to eliminate this one, the last one, plus of zk plus 1. Just eliminate this part, please, because step 2 doesn't say this. So as I was writing this one, I just have made something wrong here. So please avoid this one, and again this one. So from step 2, we have, you see, the sum from z1 up to zk bar, which is actually this one, to be equivalent to, you see, the conjugate of, you see, these complex numbers from z1 up to zk. You see, forget about this one. So from this now, let's assume that the sum of these k complex numbers from z1 up to zk to be w, where w is some complex number. You see, here w is a complex number because the set of complex number is closed under the operation of what? Addition. Whatever complex numbers you may add, you see the result is again a complex number. So w is a complex number. So what follows is this one. Look, as you are adding these complex numbers from z1 bar up to, you see, zk bar, we can have w bar. So w bar plus zk plus 1 bar can come. You see, you can have this one, guys. And from this, look, we can have this to be equivalent to this one according to step 1, because step 1 said that, look, step 1 said that whenever you have z1 bar plus z2 bar, two complex numbers bars under, you see, summation sign, this can be the same as the conjugate of z1 plus z2. Here we are having bars here, so you can combine these two as w plus zk plus 1 having a bar above. You see, this actually is directly taken from step 1. We have just proved that one over here. So what we can have next is w is nothing, but it is equivalent to 2. You see, here it is the sum of these k complex numbers z1 up to zk. So copy this one indirectly, you see, paste here in place of w, so we can have this one. So look, zk plus 1 is obtained here. So what we were, you see, planning to see has been obtained here. Look, our interest was to know this, you see, to show this one. So here we obtain that. So we can say that, you see, p of k plus 1 is also true. This by the principle of mathematical induction, the statement that says, you see, the conjugate of the sum of n complex numbers is equivalent to 2. The sum of the conjugate of each complex number, each n complex numbers is right. So this proves, you see, our mathematical concept or statements.